All right, today we're going to look at the first quiz from the second semester of organic chemistry for spring of 2019. And we're going to be looking at, it's about the first half of chapter 11, where we're looking at the reactivity of alcohols. Let's take a look at question number 1 there, which is just the basic, covering the basics of some of the reactions that we've talked about and covered through the first half of this chapter so far. So looking at the top left-hand side there, let's zoom in here, right? We have an alcohol, and we're reacting that with sodium dichromate and sulfuric acid. So this is the basic setup that we look at when we're looking at oxidations. Remember what I said to take a look for, right? We have some kind of, let me change pens here real quick. We have some kind of transition metal here that is in a highly oxidized state. We have sulfuric acid around, and we can assume if we have sulfuric acid, we're going to have some water around in this setup also. And so this is a standard setup for an oxidation. So once you identify that we have an oxidation, the next thing to do would be take a look at the alcohol itself, right? So we're looking, let me use a black pen here, right? So we're looking right here at that carbon. We identify that carbon as a secondary, and if we have a secondary carbon, right? If we have a secondary carbon with an alcohol, all we can do when we oxidize that is take it to a ketone. Okay? So remember, if we have a secondary carbon attached to our alcohol, the best we can do is take this to a ketone. And that's what our product's going to be, right? We're not going to worry about the double bond over there. We're going to end up taking our alcohol to a ketone. All right? Let's scroll over here, take a look at this, and see what's happening. It's asking us to fill in the reagents needed to do this transformation. We see we start with an alcohol and we end up with an aldehyde. Now that's going to be indicative that we need to set up one of our reaction conditions that does not have water present, right? So we need to run an anhydrous oxidation if we want to give it that terminology. So we need to pick one of our conditions that does not have water around to do an oxidation. And there's quite a few of them. There's quite a few answers that you guys could put here. We could have put DMP, which is the Des-Martin periodane, right? That's that weird looking cyclical iodo structure that's got a bunch of acetates bound to it. And you can take a look at your notes or in the book and you can see the structure of that. You could have used PCC or PDC. That's pyridinium chlorochromate or pyridinium dichromate. Those are the organic soluble chromium compounds that can do oxidation without water present. And then we have our Swern oxidation, which is usually the go-to oxidation. And the Swern oxidation is usually the go-to when it comes to actually doing an oxidation in the lab. Remember, the Swern oxidation is where we have this setup here. And we usually put that COCl2 compound with DMSO, and then we finish up with some kind of organic base to complete our oxidation here. Right? So the basic setup for a Swern oxidation looks something like this. But any of those answers would have been perfectly valid here. The whole point is when we have a primary alcohol, right, primary alcohol to an aldehyde, that is where we have to be mindful about what the oxidation conditions are. Okay, so here's our review question from last semester. HBr, we identify a strong acid. We have a double bond, so we're doing an addition reaction. If we have an acid, we're typically going to go through a carbocation intermediate, right? So let's see if we can quickly work through the mechanism here, right? We have HBr. I'll use purple here. So the double bond is going to swing open to grab that. This is an asymmetric double bond, so we have a couple different products that can get produced here. Let me find a black marker. That looks good. So depending on which way our alkene opens up, we can end up adding our hydrogen here, which leaves our positive charge here, right? Or wrong color, wrong size pen there. Or we could end up with this product here, where we have our hydrogen bound here, and we have our carbocation over here. Okay? So let me pause here real quick. Let me put a quick, right? If I just identify these with red and blue, right? Blue, blue, red, red, right? If we have an asymmetric alkene, remember, we can put the cation at either one of those. And in this case, it's going to end up leading to different products, right? Let me continue this one in red here. Let's take a look at what happens with the product of this one. All right. So we have this carbocation. We look next door. We're not going to be able to do any rearrangements, really. So the carbocation is going to stay there, and we have our bromine then come in. Our bromine's going to come in and send a bond right there, which means we're going to end up generating this. Oops, let me go back and just put this in purple here, so we can, right? So just to, so that we're consistent with colors here, right? So we've got that compound there, but we have to pause and think, right? We have to pause and think. That carbon in red is now a chiral center, right? And remember, when we go through a carbocation, you're going to make both, or you're going to make the set of enantiomers. So we have the wedge and the dash of our product there, right? So we have the R and the S. So for what it's worth, right, we have the S and the R version here, okay? Good practice to remember how to do S and the R and the S and all that kind of stuff. So that is coming from our red intermediate there, okay? Now we take a look at, we'll continue on with the blue one here. Right? So I'm going to continue on with the blue one here. So here's where we left off. And we have a carbocation, so we pause and we say, can we rearrange or shift to make a more stable carbocation? If we look right next door to that blue carbon, right, we should see something that's unique. Or maybe not unique as a term, but maybe we should say something that's a flag that we should pay attention to. So we see a quaternary carbon next door to a secondary carbon. So that's pretty indicative of an alkyl shift, right? So we're going to shift our methyl group. Right, so we have one methyl group here. And I'm going to put the shifted methyl group in purple, right? So that's where our purple arrow there comes up. And then now our carbocation is there. We did our shift, the carbocation's most stable position at the moment. And now we can bring in our bromine, and that'll lead us to our product. Let me just continue with the colors here then. There we go. Okay. And I'll just mark this as the product from the blue line there. All right, so we end up making 3 different products as we go through this. Now the product from the blue line there, right, is not a chiral center, so we don't have to worry about R or S. Okay? But HBr, an addition reaction to an alkene, right, goes through a carbocation intermediate, pay attention to shifts, movements, and then pay attention to whether we have a chiral center formed at the end. All right, moving on to the last one over here. DMP, right, that's our, we talked about it in the problem just above this, Dis-Martin periodine. That's just one of our oxidation conditions, and it's a water, it's in without water oxidation, right? So we can stop at an aldehyde. So we turn our primary alcohol there to an aldehyde, and we turn our secondary alcohol into a ketone, right? If you take a look at the instructions, I said assume an excess of reagents And so we'll turn both of those. Okay. Simple, straightforward, nice. I like it. Okay. So let's take a look at our mechanism. If I can scroll my screen here. Okay, apparently I can't scroll my screen, so that's a good sign that I'll pause this video and I'll go carry through with the mechanism in the second half here once I fix whatever technical issue I'm having.